So the structure of my talk is, since a lot of you have probably not used Julia before, I was going to introduce a little bit about the language itself and give you guys a feel for what it looks like, and speak about what it took to come here, and what it, where the direction in which we are progressing and where we are going forward. And then I will, so I'll be showing a few slides, a few demos, and a few things on various of our websites, and I think that's how I'm going to structure the talk. Do you guys do questions afterwards? I'm happy to take questions during the talk. I may not answer them all, but please feel free to interrupt me and ask a question, and I'll be happy to answer it either right away or after the talk. All right, so I'm gonna go full screen. Hopefully that's fine. Okay. So I'm going to start off with, all right, so why one more programming language, right? That's what, many of you might be wondering, why one more, right? But then it's a question that you can always ask about the language that you learned, right? Why did the person or the group of people create that one, right? Why are you using Python? I mean, why not just use, SAS or Fortran, right? And so, languages are all about abstractions. It's about how easy it is, they're abstractions for communicating with the computer, right? I mean, and the easier the abstraction, the higher performance the abstraction, the better off you are. And we did a poll of a variety of different languages, right? These list of languages that you see in this word cloud actually are all dynamic languages for the most part. So you will not see C++ in this list, for example, or Java. Just in the space of analytical languages, right? Languages that you use for some form of analytics. Over the last 40 years, there have been these many. And there continue to be more, Julia being one of the most recent ones in this trend. And many of them come and go. Many of them are commercial, some are open source. But what they share in common is that they're dynamic. They tend not to feel like C or Java or C# in the way you program them. They tend to be dynamic. You don't have to specify types. They tend to be interactive, and they tend to be sort of at a higher level of abstraction, so that as a data scientist or a mathematician or a quant or an actuary, a physicist or scientist, you will be able to work with the right mathematical structures in a way that's intuitive, right? And so that's how we started out. Now, when we started out our work on Julia, the reason that motivated us was the two-language problem. And the two-language problem, simply put, is there are languages that are high performance and there are languages that are productive or easy to use. So a language like Python is very easy to use. You have an interpreter, you just get going, and it just feels intuitive and easy. However, it does not give you very good performance. Python derives most of its performance from calling libraries written in C. So as a result, as a Python programmer, you are going to write a native Python library, you might often find yourself limited by the speed of the Python interpreter. And there are many things that are being done to address it, but that's not something I'll delve into right now. But suffice to say that there are languages like whether it's Python or R or many of the dynamic languages, they often tend to be interpreter driven and slower in execution compared to statically typed languages like C++, Fortran, Rust increasingly, and all these languages, which tend to be very high performance, but then they require you to write a lot of code at the lower levels, right? So what do you want out of these, right? So you have the option of either easy or fast, but never both at the same time. And that's sort of what motivated us to start our work on Julia, that we felt that we need a system that is simultaneously easy to use and gives high performance. And in order to do that, we decided that it was not going to be possible to take an existing language and add performance to it, right? So we could not have started with Python and added performance capabilities, some compiler magic to it, and make it faster. We felt that we needed to start out with a clean slate and build our own programming language. And a lot of people ask me, like, why can't you just do that, right? Why can't you just, sort of bolt on newer techniques onto an existing language? Everyone knows the existing languages. And I often ask the question that, if you wanted to go at high speed, would you take a Fiat car and put a jet engine on it, right? or would you design a Ferrari, right? I mean, if you want performance, you have to design for performance. You can't take something that was, designed for a different purpose and then, strap on performance at the end. So that's why we started Julia. We wanted something that we were fully in control of. We could drive the design and we could actually take it in the direction that we thought would be interesting. I'd like to point out, the reason I like to point out the prizes is, so many of us have received prizes over the years now for our work on Julia. And the reason I like to point this out is simply because people think that if you've received a prize, it must be good, right? But so for me personally, the James H. Wilkinson Prize that we received this year was quite impressive, because it's a very hard to win prize, because it's given out only once every 4 years, and you have to get it within the first 10 to 12 years of your career after your PhD. So you effectively get only 2 to 3 shots at winning the Wilkinson Prize, and it's given to people who've written the best of numerical software over the years. My co-founder, Kenno Fisher, thank you. Thank you so much. So my co-founder, Kenno Fisher, was awarded the Forbes 30 Under 30. Professor Alan Edelman is a recipient of many awards, one of my co-founders again, and for his work on Julia. But the prize that I really feel really excited about is the prize for this system called JUMP. By the way, did any people find the JUMP stickers? Now, JUMP is also a NumFOCUS project, and I have some of the JUMP stickers as well as the Julia stickers. So Miles, Ian, and Joey, created the JUMP library. JUMP is Julia for mathematical programming. It's a library that you use that is available to Julia users for doing all sorts of integer programming, convex programming, optimization, all kinds of fun stuff. But it's a library that's written in Julia that's best in class, and that for which no comparative solution exists anywhere else. So today, if you want to do the best form of mathematical programming, Julia is your best bet. And increasingly, for many kinds of domain-specific libraries in scientific computing, in numerical computing, in data science, Julia is the only place where you can get the best libraries. And so it was really heartening that to see that other Julia projects themselves are being chosen by their respective communities as leading the light. That was the citation for our prize, but I'm not going to dive into it because this is the topics here are what most of my talk is about. Now, at this point, I'm going to sort of switch into a demo, because the software 2.0 stuff and the differentiable programming, which is the main topic of my talk, is something that we are working on now, and that's some of the future directions for us. But in order for me to talk about the future, I should first talk about what Julia is as a system. So let me do this. All right. So what I have here is a Julia session and a Python session. And I'm going to do a very simple thing. So I just, right before this, right before my talk, I put this little snippet of code together. And I like to use it. It's actually trivial. Everyone can just see it and see what's going on. It's just calculating. Is this visible all the way at the back? Yeah, I see some heads nodding, so I'll take that as a yes. So this is just a simple piece of code that's computing the sum of a vector. The simplest thing, it's initializing the sum to be 0, and then it's iterating through every element in the collection. In this case, it's going to be a vector, and then it's adding it up and then returning the sum. The simplest possible calculation. Would you ever write this in Python? I mean, I think the answer is obviously no, otherwise why would I show it, right? So this is a code that you would never write in Python, and the reason is that it would be extremely slow, right? So let's see, I've imported NumPy here, and I've created a vector of size of 1,000,000, and I'm just going to time this, and it takes about 200 milliseconds. Now 200 milliseconds doesn't sound like a lot, but if you're just summing 1,000,000 numbers, that's actually a lot of time. So, here's the same in Julia. This is what the Julia syntax for it looks like. And I have my, random vector of size 1,000,000 here. And I'm just going to sum it, right? And it takes about 1.8 milliseconds. So this time is in seconds. This time is in milliseconds here. And so if we divide 207 by 1.8 milliseconds, it's about a factor of 115, right? So Julia, for this simple example where you're just going and writing a for loop that's adding every element in an array, Julia turns out to be about 100 times faster than Python. And why is this the case? And the reason is because Julia actually has the JIT compiler under the hood. So it actually figures out the performance, it figures out the types of all the variables in your program. And once you know the types of all your variables, you're able to generate very high performance and efficient code and run it fast, right? So this is the basic story for performance, right? That the computer needs to know everything about your program in order to produce high performance code. The humans hate writing everything, right? I don't want to write, S is a double precision floating point number, and A is a vector of double precision floating point values for input. I don't want to write all that. I just want to write the minimal stuff I want and get on with my life, right? And I don't want to sort of write everything in great detail. And that's what abstractions is all about, right? The higher the level of abstraction, the faster you can, you can work, the closer you can work to your domain. And that's the difference, right? So Python gives you the ease of use here, but Julia takes the same ease of use, adds a bunch of compiler magic to figure out all these hard parts, and actually gives you high performance. So one of the cool things you can do in Julia is you can actually look at the generated code. So this is the assembly that was generated for the Julia sum function, right? So at the end of the day, why does a program run fast? It's because it's doing the least amount of work. On a computer, often the least amount of work means the tightest code that you could write, right? What's the fewest number of instructions that you could execute in order to get your running time low, and that's what it looks like here. A lot of this is actually just setting things up, but you can see the addition happening here, right? You don't have to be an assembly programmer to sort of appreciate this. In fact, when you program in Julia, you almost never look at something like this. It's mainly for for people who really are keen about the last bits of performance. But I kind of make two observations here, right? So it's kind of doing what you'd expect it to do, but it's also generating these vector instructions, right? So the V is the vector instruction. So modern CPUs, as everyone knows, have run through the Moore's law, right? You are no longer getting higher performance from a newer CPU. How many people thought they bought a new laptop after a few years and found it to be running roughly at the same speed, right? Just about everyone, I would think. Single core, single threaded performance simply has not gone up and probably will not over time. So the only way to get high performance is by using vector instruction sets, so operating on multiple pieces of data at the same time, or, well, not or, it's an and, multi-threading, right? So using multiple cores. And the factors can be, like on a modern Intel CPU, the difference between single-threaded, single-core performance and multi-core vectorized performance can be a factor of 100, right? So it's very important that the system that you're using and the compilers that you're using are aware of this. Now, Julia has been able to do some form of auto-vectorization over the years, and you can see it in this simple example. With Julia 1.3 that we just announced a couple of weeks back, so we had the Julia conference, JuliaCon, about 10 days ago in Baltimore near Washington, DC, and we announced the Julia with multi-threading. So Julia is now the first high-level dynamic language with multi-threading. So imagine writing Python, but having the full power of multi-threading at your fingertips. It just allows you to get levels of performance that were simply not possible before. All right, so with this, I think I'm hoping that I've given you a little bit of a feel for what Julia feels like, right, or looks like. It's simple syntax. It is interactive, so I can go ahead and do things like generate 10 normally distributed random values, or I can sum them, or I can do all kinds of things. If I wanted to do the square root of the answer of the sum, whatever. So it's an interactive system, but it's also high performance, and that's what sets it apart. So this is really the foundation that we started out with, right? It's a foundation of having a system which has which has a bunch of these amazing and interesting libraries. Actually, let me, go to those libraries next. So I'll switch back to my talk here now. Okay, so with that sort of basic introduction to Julia itself, I'm going to, now sort of tell you a story about, where we are heading and show you examples and use cases of what's going on while simultaneously talking more about our ecosystem. All right, so, all of you are data scientists here, and all of you have heard about these phrases around software 2.0, deep learning. Everyone's heard of deep learning. Can I see a show of hands of everyone who uses this or has heard of it at least? Okay. How about the phrase differentiable programming? So maybe a couple of people have heard about it. Now, so that there's a quote right there from Yann LeCun, who recently got the Turing Award for the highest award you can get in computer science for his work on deep learning, and he said deep learning has outlived its usefulness as a buzz phrase. And what we really want is differentiable programming. So what is differentiable programming, right? The fundamental concepts behind deep learning, what makes deep learning really work, right? Is, you have these neural networks, and fundamentally there are two things that are going on under the hood. There is automatic differentiation. So you're able to take, you're able to feed your program lots of data. You're able to sort of compute derivatives of your program, figure out, how your observed data is, compared to what your predictions are. And then, if you're really off, you use the derivative to sort of, fine tune your neural network so that it will make a better prediction, right? The key thing is derivatives, right? So derivatives allow you to sort of, find the correct search direction in a way that will minimize your loss or your loss function. And the question is, so in deep learning, all you do is take derivatives of programs that are fundamentally neural networks and not very much else. But what if you could also differentiate any program structure beyond neural networks? What if I could differentiate, what if I could differentiate my differential equation solver? What if I could differentiate my GUI? What if I could differentiate through my database, right? Query optimization for databases, for example, image renderers, right? All kinds of things that we work with, data structures. What deep learning has taught us is that if we have a way to differentiate, we can optimize, and we can get, we can have the models and the programs do things automatically instead of humans writing every little bit of code, right? Everyone used to do image segmentation using these, image segmenting algorithms before deep learning. It used to be error prone. It used to be difficult work. But now with deep learning, you don't care about it, right? You just feed the program lots of data and it spits out what you want. And it turns out, so you can generalize this technique a fair bit beyond neural networks to more general program structures. And in Julia, we've sort of taken it upon ourselves to develop Julia in a way that it's able to differentiate through as many different kinds of program structures as possible. And I'll be showing some demos of some of this stuff. So Andrej Karpathy, who's the director of AI at Tesla, sort of coined the phrase software 2.0, in which he said that the way we move forward, the way we program going forward is increasingly going to be about, using models and data, and not so much as sort of writing programs tediously and manually, by hand, taking care of every little, corner case and condition. Instead of that, we are going to sort of be data driven, and he said this is software 2.0, this is how things are going to be. So if I'm building a self-driving car today, I don't go about, writing a code for every possible thing that the car might see. I just drive around a lot and generate tons and tons of data, and then build models that will learn from that experience, right? And that's the software 2.0 world. The path towards differentiable programming is basically, so as people have applied machine learning in increasingly new domains, the programming languages communities have figured out that the best way to bring the benefits of deep learning to a larger set of programs is by implementing those ideas not in libraries, but in programming languages themselves. So not just in TensorFlow or PyTorch, but in a language like Julia or Swift. So Chris Latner, who was the original designer of Swift at Apple, is now working on creating a differentiable system called Swift for TensorFlow, the only other system that's actually apart from Julia, that's focused on differentiable programming. All right, so we've been presenting this work a fair bit. I'm going to sort of, just mention, so TPUs, that reminds me. So we spoke about automatic differentiation. So that's one part of the story, right? Calculating derivatives and optimizing your programs. The second part of the story is performance, right? So GPUs give us the best performance today. So in order for you to run your codes and your learning at scale, you need to be able to target new hardware. GPUs are, of course, from NVIDIA that everyone's using. TPUs are from Google. They're called tensor processing units, and they run at extremely large speeds for doing many kinds of linear algebra operations, and which makes them, they were designed to run neural networks fast, and linear algebra is sort of what you're doing under the hood. So Julia runs on GPUs natively. You can write your Julia program and execute it on a GPU with little effort. Julia also runs on TPUs. Zygote is a key part of our differentiable programming stack, as is Flux, and I'll speak a little bit about them going forward. So to complete the discussion around differentiable programming, here's a very simple example. Everyone might remember the rules of how derivatives are calculated from college or maybe even school days, right? You have your chain rules, and if you apply the chain rule repeatedly across expressions, you're going to calculate a derivative. It turns out that you can actually apply these same techniques to computer programs so that you can differentiate not just formulas or expressions, mathematical expressions, but also entire program structures that include things like for loops and if statements and function calls and all kinds of stuff. But at the end of the day, what's happening under the hood? So we have a function foo here is just doing some multiplication operations, a tanh and a plus, nothing complex. But if you want to calculate the derivative of this program automatically, right? So as a human, if I gave you that program, you could have written down those derivatives on your own. You could have just written down on pen and paper, gone line by line and done it. The same thing can be done by the computer by doing source-to-source transformation. So the Julia compiler can parse that program, can understand and reason about it, and produce this program on the side, which not only evaluates the function foo here, but also the gradient of foo, or the derivative of foo. And that's exactly what it takes to calculate it. The key is doing it automatically. The moment you can do it automatically, you have raised the level of abstraction, and now you can apply these techniques not just to neural networks, but to a broader class of problems. You might be wondering, why is this important? Why do we need to go beyond neural networks? Right? Neural networks have been very influential. They've solved a lot of interesting problems in vision, in speech, in natural language processing, and these few improvements by themselves have sort of led to a revolution in, they've given us self-driving cars, they've given us, Alexa, they've given us all these amazing products today. Well, self-driving cars not yet, but maybe they'll come soon. And we don't yet know when they'll come to the Indian roads. So there's also that problem. But so the reason why going beyond neural networks matters is that the more you can tell your models about the underlying physics or about the underlying science or about the underlying dynamics of your system, the lesser data and the lesser compute power you need to train them. So for example, in most of the things out in the real world, there is an underlying scientific phenomena that explains it, right? If I'm pricing an option, there is actually a mathematical formula that tells me what the option is. If I'm using deep learning and not using the information, the mathematical information I have that describes the program, I'm actually going to end up spending a lot more time and energy exploring parts of the search space that are not relevant for solving the program at hand. And this is why differentiable programming really comes into the rescue. So I'm going to put a pin out here in differentiable programming and talk a little bit about applications of Julia going forward next. Oh, sorry, there we go. So keep these 2 points in mind as we go forward: automatic differentiation and running on high performance hardware. If you can do these things, you can solve all kinds of interesting problems that are not possible to solve today. Celeste is a project that it's an astronomy application that we ran in Julia. So a lot of people ask us, right, okay, it's got a lot of interesting compilers, it's got some nice technology, it's got performance, but can I do anything real with it, right? Maybe some of you have been thinking that. So the answer is yes, we've done lots of real things with it. The Julia community is very large today. And I apologize for not being able to see this image. This, there's a little bit more detail here, but it's getting washed out by the contrast, which is fine. Celeste is a project that scanned, that took the data of the Sloan Digital Sky Survey. So a telescope that scans every part of the visible sky. And the goal of this project was to detect every visible object in the universe, at least visible to that telescope that was scanning it. And so it's a vision problem. And it turns out that a specific machine learning algorithm had to be created in order to process that data set. And it took, we processed this on 650,000 cores on the world's 5th largest supercomputer. It's called Cor. It's at Lawrence Berkeley National Laboratory. And what makes this problem incredibly challenging is that, if you see something like this in the image, you can kind of think like it might be a galaxy or something. Or if you have a little thing like this, maybe that's a star. But there's a little faint red dot here, which unfortunately is not very visible right now. But the question is that actually a visible object, or is that just an artifact of the instruments? Is the instrument just operating at its detection capability, right? The instrument finally cannot see everything. It's all a matter of what signal was produced and how to interpret it. And that's what the machine learning algorithm in this paper does. It applies an optimization problem across 180 million objects in this data set and processes them and then creates a catalog of the visible universe and uncertainty estimates for all of them. Turns out these things are not easy. So, when you're working with NumPy, when you're working with SciPy, or even when you're working with, like default array constructors in Julia, you get very nice data structures. Your array is laid out in memory. The columns are all contiguous, and it's very easy to work with that regular data structure. But when you're running at this scale, 60 terabytes of data is a lot, by the way. And when you're running at that scale, what you get is, you can't lay out the matrix in a very trivial format that's easy to work with. You have to lay it out in a way that makes it easy to work on in parallel. And Julia makes it possible to sort of, represent data in all these interesting, new formats and, matrix structures and storage formats and whatnot. This is a whole topic by itself. But what I wanted to point out is that Julia is flexible enough that you're not limited to working with the data structures that are provided to you from the system out of the box. You can create custom data structures and user data types and still get the highest levels of performance on these things. So this is a little bit about what the GPU program looks like in Julia. So if you program CUDA, you might recognize some of this. You can write CUDA natively in Julia itself. You don't have to write the C++ CUDA in order to make it run. You can write CUDA itself in Julia, and it runs quite well. This is the assembly that is generated directly from the Julia compiler. And by the way, I have these citations for all the slides, so about where the data on them comes from. So in case you're interested, you can follow up on these things. All right, so CUDA in Julia is as fast as C. Sometimes it actually performs slightly better than NVIDIA's CUDA implementation, but I would say by and far they are on par. Again, remembering that running on high performance hardware is essential to performance and essential to doing differentiable programming. This is Julia running on TPUs. We've been able to scale it to a complete TPU pod, and the TPU pod is about 100 petaflops. I think we were able to get 4.3. I might be mixing up some numbers here. Let me take my numbers back. But we've been able to get multi-petaflop on basically a large TPU pod as well. Jeff Dean at Google was quite excited when he saw that, and he tweeted about it, that Julia and TPUs are equal to fast and easy expressible ML computation, right? And the story is straightforward, right? You have the best hardware, you have the highest level of abstraction, you're not giving up performance, but you're still retaining the ease of use, right? It's the same message, going forward again and again. Here's a comparison of various deep learning libraries, right? That's TensorFlow right there. It's largely written in C++, and some of it is in Python. And the same story applies to all of these things here. And Julia, so Flux is a Julia-based deep learning library. It's actually incredibly small. You can open it up and look at the source code behind it and read about it, and it's 100% in Julia. and it runs on GPUs and TPUs and all kinds of stuff. So Julia is actually able to, to me, this is the most interesting thing about this slide, right? So we have two Julia libraries here. There's Knet, which is mostly in Julia. That was written before our CUDA native packages existed, so it has a little bit of C++ code that calls CUDA. But Flux is 100% in Julia, and it gives a fairly good performance on the common problems, and it's the right level of. So what I wanted to say was it's only a few hundred lines of code, so it's great for teaching, it's great for opening up under the hood, it's great for modifying. And we have a few pre-trained models in our model zoo that you can get started with. All right. So moving forward with differentiable programming, right? So if you believe the story that, deep learning is going to be generalized, is, new hardware is going to keep on coming online. The question is, what does Julia have to offer in addition to the basic constructs? And the answer, in order to make it easy to do differentiable programming. And one of the things that we are trying to do is have our differentiable programming stack work not just on the Julia language, but also on a lot of the packages in the Julia ecosystem. So Julia has the best-in-class packages in many domains. We have some of the best differential equation solvers if you come from a scientific background. Some very good graph processing tools. I already spoke about JUMP, which got the prize. Libraries for data science, image processing, computational biology, deep learning. These are just a few of the projects that have interesting looking logos, so I could put them on this slide. But there are about 2,500 Julia packages out there, and many of them are very high quality. The Julia data ecosystem, for example, is a completely fresh take. So if you come from Python or R, you will find yourself right at home, but you'll find many new things. So for example, in Julia's data ecosystem, so often you don't even need to use a package like JuliaDB or data frames in order to process your data, because you can create user-defined data types, load your data, create your own sort of struct of arrays data structure, and just start processing it at incredible speeds. But if you have sort of a more regular CSV file, you want to load it, you want to analyze it quickly, you want to run sort of something like XGBoost on it, let's say, or even scikit-learn, you can do that in Julia, by the way. Also, I should have pointed this out. You can call any Python library from Julia by just saying pycall, by calling it through the pycall package. Let me see if I can. I didn't try this out before, so I don't know if I've set up all my environments correctly, but let's just try and see if it works fine. All right, so let's see if I say using pycall. I have not installed this package. I'm going to be adventurous and try and install it right now. So let's see what happens there. Okay, so let's make it a little bit larger. All right, so if I press the right bracket key, the right square bracket key in Julia, it activates my terminal, my package mode. And now I can go and say add pycall. So what Julia is doing is now updating the list of packages and resolving them, and hopefully it's not going to try and download Python. All right, so it's doing its thing. The Julia package manager is, I think, one of the nicest things about Julia. It's unlike Python's package managers. I think Python has a variety of package managers, and it's kind of been incredibly hard in the Python ecosystem to sort of pin down versions, to have reproducible programs, and to work with packages in a predictable way. I think Anaconda has solved most of these problems today, but it's taken a long time. We've done our homework from the experiences in the Python ecosystem, and try to build a package manager that does not have those issues. All right. So now I exit the package mode and say pycall. Let's see what happens. So the first time you use a Julia package after downloading it, it has to be precompiled. And a lot of the smarts about Julia are at compile time, right? So you have to pay the cost of compiling a program in order to get its performance. Now, a package like PyCall is fairly large, so but there it is, it's come back. So now I can go and say so let's just do this. Right, so add py import math. So I have now I have imported the math package, and I can now go, let's see, is it math.sign? So math.sign is the built-in Python sign function, and I can go ahead and do sign of pi, which should be almost 0. And so now I'm calling math.sign of pi from Python inside of Julia, and I can compare it with Julia's built-in sign, and they're the same thing, right? So we are able to call almost everything in Python from Julia. So you can call matplotlib from Julia, and it's a package called pyplots.jl that lets you do that. And you can just about call any Python function, any R function, any C function. Actually, let me show you how easy it is to call a C function from Julia. So oops. All right, so that's calling the clock function from the standard C library. It has, that's the name of the function. That's the return value. It's an int32, and no input arguments to this function. So note that I did not have to have a C compiler run through and compile some kind of a program and load it before I could call it. Julia actually has complete interoperability with C and C++, and you can just use it interactively from the command line. Now, one of the things that we care about a lot in Julia is composability. And composability, what does composability mean? Oh, so by the way, this is a screenshot of the Julia Atom-based IDE. It's called Juno. And, so it's got, it's got your usual IDE kind of stuff in here. It's got, that's your code. That's the result of running the code. So it's the printout, the printing that happens on the terminal. And then that's a graph that's updating in real time. And what's happening here is we had some data that was blue that we are fitting using a neural network. But the neural network is not your standard neural network in this case. It's, one of its layers is actually an ODE. And it's trying to learn, let's see, it's trying to learn a standard, let me see if I can tell right here. If I remember this correctly, it's trying to learn a standard predator-prey model. So, it's usually like foxes and rabbits is a standard predator-prey model, right? If I have a garden with lots of foxes and lots of rabbits, and then each time step, the rabbits can either multiply and the foxes can either eat the rabbits, and then you can kind of, if there are too many foxes, they'll eat all the rabbits and then die off. If there are too many, rabbits, then there isn't enough space for the foxes. So you sort of get all these interesting dynamics, in which either everything can go to 0, or it can kind of shoot off, or you can get equilibrium where, the foxes eat off just enough rabbits and the rabbits multiply just enough, and, you get some very interesting, steady state equilibria there. And they're typically modeled as ordinary differential equations, but the fun thing is you can now put these kinds of equations and structure into your neural network and then apply it to, data fitting problems, specifically in problems that have a scientific, origin, right? All right, so the reason I brought this up is I wanted to introduce the differential equation package called diffeq called differential equations.jl here. This was written by Chris Rackauckus, who is now teaching mathematics at MIT. This package works with Julia's deep learning library Flux. Flux and differential equations did not know anything about each other, right? Two separate authors wrote their packages for two completely different purposes. But in Julia, it composes because of the way the language and the underlying frameworks work. And so this is making one layer of the neural network and a differential equation, and then it just runs. And the combination is presented in this paper, in this package called diffeq flux, which is the combination paper. All right. So that's what composability is all about, right? That things that were built by different people can actually come together and work together. Here's one of my other favorite examples, a package called measurements.jl that allows you to capture error bars on anything that you're doing in Julia. Written by Mose Giordano, who's a research software engineer in the UK. Chris, obviously, like I said, is at MIT. These folks had never talked to each other, and these packages were not written to work with each other. But it turns out that I can now create, so the measurements package allows me to use this syntax right here. So, G is the gravitational constant, 9.78, and I do plus minus 0.02. So that's the uncertainty in the input, right? I may not know the value of G 100% accurately, so I have a little error bar on it. By the way, Julia allows Unicode, so you can use all kinds of funky Unicode symbols in your programs. You can even use smileys and assign values to a smiley cat or whatever, and then add them. I wonder if I can actually do that. Let me try that. I don't know how to do that on the terminal. So you can do \alpha tab, and I can get alpha, right? So I can do this, but I don't know if I can get a smiley cat. Let's just see. Yeah, I don't think that works. All right, but let's go with the alphas, right? So slash alpha, and I can now go \_2, so that gives me a subscript, and I can go \something 3 like that and get a superscript, and now I can assign it a value, and I can go on. If I do pi, sorry, let me do this again. If I do pi, then I get the math constant pi, and notice that this is represented as a dot dot dot. Oops. This dot 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 there, which means it will actually be calculated to the right precision automatically when you use it in an expression. So which is kind of cool by itself. All right. So full Unicode basically that can be used in your program. So you can write your comments in any Indian language, for example, should you want to. I think we all tend to program in English, so it's not a problem. But I think for folks for whom English is not a first language, having this allows for even documenting in their native languages. What I was going to say here was the composability with measurements.jl. So I have a regular ODE problem solver, and then I can propagate these uncertainties through it automatically all the way into my plotting package and get these error bars that you're seeing all the way. It pretty much just goes through and through and just does what you'd expect. So composability is a feature that comes across Julia. So when you do differentiable programming in Julia, you get the benefits of all this composability. The things that were never designed to work with each other actually do end up working with each other because they all speak the common language and of Julia under the hood. And I think that's quite powerful. So I'm going to skip through a few slides and try to get to a few more applications. There was a Boston school bus optimization challenge issued by the Boston public school system, and a team from MIT actually helped optimize the routes by using the jump package that I talked about earlier. It saved the school system about $5 million through the optimized bus routes, and the story was featured in the Wall Street Journal. So I think that was pretty impressive use of Julia there. More recently, there has been a new climate simulation collaboration that has been announced between MIT and Caltech that has decided to use Julia and Julia's GPU capabilities all the way on some very large high-performance computers. There are increasing amounts of Julia usage for a bunch of research into energy, and especially in moving towards renewable resources. A lot of Julia applications in banking and finance. For example, Aviva, one of the world's largest insurers, uses Julia for its Solvency II system. It's basically a risk management platform, and it uses Julia to simulate all the future scenarios that might happen and figure out if the company is going to be at risk in case the stock market crashes or something. BlackRock uses Julia for its analytics platform as part of the Aladdin analytics platform. The New York Federal Reserve, for example, uses Julia for a lot of its macroeconomics research. In the field of pharma, Julia is used. So this is a software called Pumas that we just announced very recently, along with a couple of folks at the University of Maryland at Baltimore. We are now combining machine learning techniques with some of the traditional pharma simulation software and using it for precision dosing. So, you know, a lot of times in the hospital, it's important that you're given the perfect dose for, you know, for the treatment you're receiving, right? You know, everyone knows that dosing, you know, you don't get personalized doses today, right? You just get the same dose. You know, you might get like one for an adult male or an adult female. Children get different doses, but otherwise it's the same, you know. But, you know, why shouldn't doses be personalized, right? I mean, you know, everyone's bodies are not the same. And often in cases of like, for example, antibacterial, in cases of, you know, drugs that treat bacterial infections, right? So it turns out that giving too small a dose will not, you know, will not get rid of all the bacteria. And if you give too high a dose, it's going to be bad for your body. So it's important that you give the right dose. And that's, you know, one of the things that we're working on with, for precision dosing here, I think. I have a bunch of slides here around the details of what's inside of Julia and how it works, but I'm not going to be able to do any of that right now. By the way, the type system in Julia has been formalized and been rigorously proven. So that's what these two slides are talking about. I just love looking at them. They look kind of crazy and difficult to read. But if you're into this kind of thing, you can read these papers. Topic bfloat 16. So bfloat 16, by the way, are the new floating point representations that are used for machine learning, especially. And you know, the intricacies of floating point deserve not just a whole talk of their own, but probably a semester-long course. And there is no end to the amount of fun you can have with floating point arithmetic. I would highly recommend, if you want to learn about floating point arithmetic, to find William Kahan's website. I personally enjoy reading everything he's ever written. And he's a very fun writer as well. So let me just quickly pull it up. I'm gonna scroll all the way down to all the fun stuff. How Java's floating point hurts everyone everywhere. That's one of my favorites, for example. Or MATLAB's loss is nobody's gain. So you can kind of see these are some very nice clickbaity titles. If you're into the whole floating point thing, but the fun one is bfloat 16. So you know, you typically have 32-bit or 64-bit 64-bit precision for all your numerical things on your CPUs. Increasingly with machine learning, you know, the trend over the past has been to add more precision. But with machine learning, it's going the other way. So, you know, throw away the precision. Why? Because machine learning does not really care, you know, for things to be exact to the 15th degree, 15 decimal. But what matters in machine learning is speed, right? You have to process huge amounts of data at enormous speeds. Power is often a problem. So, you know, the size of the chip is fixed, right? The quantum mechanics is fixed. There's only so much you can produce. So in the same area, if you want to shove in more computational power and use, you know, less electrical power, what you have to do is somehow, you know, do lesser work. And one way to do lesser work is to use lower precision values. So bfloat 16 is a fun topic all by itself. But there's in Julia, there is a library called bfloat16.jl. So even if you don't have the data type in your hardware, Julia provides an emulation for working on it, so you can kind of get a feel for everything there. All right, so I'm going to finish up with a few topics about open source and contributing to open source and the community. So the Julia community has seen about 8 million downloads. It's about 2,500 packages, and it's just growing. It's, you know, I personally did all of my work on the open source Julia language in India. in Bangalore. So that's, we actually have a pretty vibrant community of contributors. So these are, by the way, all the people who have starred Julia on GitHub. That's what this map represents. So we've had a few people from Delhi and Bombay as well in India, but we see downloads from all kinds of places in India on the Julia website, and it's quite impressive, what's going on. But it is an open source project. It's folks such as yourselves, who find Julia, who write a package, who contribute, who write the tests, who write the documentation, and who made Julia what it is, right? So a lot of people often wonder who writes open source software, and the answer is it's probably the person sitting next to you, right? It's everyone everywhere, and it's not just about writing software. A lot of people ask me, how do I get started? So in Julia, for example, we have good first issue as a tag on GitHub. In order for people who are new to the project to find an easy task to help out with. Documentation is always useful, tutorials, guides. A lot of people have joined the Julia community just to contribute tests. So we have a few prolific contributors, one of whom is Katie Hyatt, who's at the Flatiron Institute in New York, and while she's a quantum physicist, her main contribution to Julia has been to improve the quality of our testing. And she meticulously looks at the code coverage of the existing tests and finds out which capabilities are not tested today, and adds those tests. And that's why Julia's quality has gone up tremendously, is because of folks like her who made this happen. We announced Julia 1.0 about a year ago, and that's when it just shot up. So that's when it shot up on GitHub right there. And it continues a very fast upwards trend. There are now a lot of books on Julia. By the way, Think Julia has an Indian edition, so there is a lower price edition here. Some of these books are only available at the full price, but there are topics. It's covering a wide variety of topics. These are some of my favorite Julia books. I really like the Think Julia O'Reilly book as a good introduction to Julia. It's modeled along the Think Python. The Think Python book, and it's very well written. And by the way, it's also available for free on the website if you want to read it in the browser. Not gonna jump into these slides yet. Julia is being taught in a lot of universities, and I'm thrilled to announce that it's actually being taught this semester at IIIT Delhi. In fact, I gave a talk yesterday to the Math and Computer Science department here. So if you're studying at IIIT Delhi, there's a class that's on scientific computing that actually is using Julia this very moment. But these are all the universities teaching Julia. These are only few of them, rather, whose logos we were able to fit on this slide. But the actual number of universities teaching Julia is probably 10x of this. So JuliaCon 2019 was in Baltimore. I do not have the latest picture. This is from JuliaCon in London last year. It's about 300 people here. We had closer to 400 people in Baltimore, and there were enough people this year that we actually had to get a drone photographer to take the picture of the entire group. So that was kind of fun by itself. So it is a community project. Please come and talk to me if you have questions about how to participate, how to join. More than questions, I would probably be happy to take ideas on how to make Julia better. And I'm going to sort of stop with this quote by Guy Steele, which I like a lot. So the main goal in designing a language should be to plan for growth. Start out small, but then the language must grow as the set of users grows. And everything I've told about Julia, right? Everything I started out with a small demos showing you, how to sum up a few numbers and showing you little assembly snippets of it. And then I sort of increasingly worked my way up using more packages and talking about the applications, and now differentiable programming, right? And each of these things has been added over time. As the set of users, as the set of applications have grown, the language itself has also grown to accommodate these things. And as more of you guys join the community, your demands will drive the next set of language features and evolution. And with that, I will stop, and thank you for being patient with me.